Hello students, welcome to my YouTube channel Data Guru Akash, and in this video we are going to talk about polynomial regression. Previously we have seen linear regression and the theory behind it. In our previous video we have also seen the theory behind machine learning, the definition of AI and Python programming language course. If you haven't watched those videos, please go ahead and look into the playlist attached in the description. Let's get started. Today we'll look into the polynomial regression. We'll understand what exactly polynomial regression is and how do we do the regression with it and when we need the polynomial regression, all the things. First, we'll discuss the theory part of it and then we'll go to the coding implementation of the same. Okay. So let's have a clear understanding of polynomial regression. So let's say if I simply have another data with me, that looks like, once again I will have one input, one output, x and y. So there we have some value, right? Some numerical value, like both are the continuous numerical value. And if we, let's say, simply create a class, the plot the data, let's say the data looks like something this. Right. So let's say if the data looks like this, and if I simply wants to, let's say, plot it, cover it by a line. So tell me which line should I draw? So this is a line, right? If you see, there are very large errors. For example, if I draw the line for this, there we have very large error. For this, we have a very large error. So the problem in this case is basically a line is not suitable, to cover this kind of a data, right? If you have very large fluctuation in the data itself, a line cannot cover it, right? If you have very, very less fluctuation, then that can be understood, that can be covered by the model with less error. Fitting a line in this kind of a data is not, will not give you very good results in case of the model, right? So choosing a line is not very, very good thing for this, right? So linear regression is out of scope in this case. Basically, even you can fit the linear regression, but linear regression itself, basically this line will not mold, right? This line cannot fold and cannot cover up all the situations, all the things in here. Okay, so that is why we need, polynomial regression. Now if you simply understand what exactly in algebra, if I write y is equals to mx plus c, this is a equation of a line. If I write, let's say, some y is equals to, let's say, ax square plus bx plus c, this is nothing but a quadratic equation. Now this quadratic equation, what we can call it as a polynomial equation, right? The same thing we can call it as a polynomial equation with degree 2. This is also a polynomial regression with the degree 1. Since degree is 1, we can call it linear because it is a linear data, linear relationship between x and y. In here, we do not have linear relationship, right? We have quadratic relationship. And similarly, I can also have some other equation. For example, ax cube plus bx is square plus cx plus d, right? So these are nothing but different types of polynomial regression. We can call it, polynomial regression with degree 2. We can call it polynomial regression with degree 3, right? Degree means, degree is nothing but the highest power of x, right? Highest power of x can be thought of as a degree. So degree basically is represents the polynomial nature of the model. If you have higher degree, so the complexity of the model will be larger. Okay, so think you might have known about this, that if you have a, let's say parabola, the curve parabola is basically a square term. The formula or the standard equation of a parabola can be squared. So there is one particular thinking that you might have gone through. I'm not sure, this was just an observation from my side, is that if you have, let's say, any equation, right, having, let's say, if you draw any 3-degree polynomial, so it will at least have 2 critical points. Now what is critical points? For example, let's say if I draw a parabola, this is a critical point where the tangent of the equation changes its sign. For example, here if the tangent is positive, so here the tangent will be negative, right? So here whether the tangent is parallel, where tan theta will be 0, so that can be thought of as the critical point. So just before that the tangent will be positive, and that's after that tangent will be negative, right? So this can be thought of as critical point. Now critical point where we can see the curve turns itself, right? So if you have a quadratic equation, the curve always will have one critical point. Like if you have an equation with degree 2, critical points will be 1. If you have an equation with degree 3, critical points will be 2. So somehow this kind of a thing you will look, right? So it's not mandatory that you will always look just here. Maybe you may look something like this as well, or you may look very, very far away as well, right? So this is something keeping in mind. We can say that if you have any equation, so it will at least have those many degree of the models. I mean, so let's say if you have a 3-degree model or 4-degree model, so you will at least have corresponding to 3, you will at least have 2-degree 2 critical points. And if you have a 3-degree 4-degree model, so you'll have 3 critical points, and so on and so forth, right? So this is basic algebra thing, or that you must know. You might be, if you were not knowing earlier. So this is something that happens in the equation of a line. Okay. Now in this example, if you see how many if we draw a curve, let's say this one, so we can simply say that this is how many critical points are there? So 1, 2. So 2 critical points are there in this. There might be more, but as of looking in the data, we can say the minimum number of critical points we can have is 2. Or if you simply create a model like this that goes through each and every data point, so there will be a lot of critical points, right? So there will be a lot of critical points, but we don't want that. That will be very, very specific to it. We never want it. This is something we call it wait a second. This is something we call it overfitting, right? So we don't want that. So okay. So this is the line. Okay. So if we take this, so we have 2 critical points. So if we want, basically, if you want to create a line, if you want to create a curve, so we will take at least 3-degree polynomial to create a curve. So instead of choosing y is equals to mx plus c, that will create a line, we will choose this particular equation, right? For this, at least I told you, at least this particular equation, I mean, where the minimum power of x is 3. Okay. Sorry, the maximum power of x is 3, right? So this is our minimum range. We can also choose a degree 4 polynomial as well. We can also choose degree 4 polynomial as well. So in case of degree 4 polynomial, how will it look like? Y is equals to, and this is just a standard equation. If we write in our case, so we write all the coefficients in W terms, like W was nothing but our weights. So for example, if I'm writing this whole equation in terms of W, so it will be W1, let's say W1, just say W0 plus W1x. This is a standard term, plus W2x square plus W3x power 3, right? Just opposite of it. So you can think of it, D is equals to nothing but W0, and C is equals to nothing but W1, B is equals to W2, and A is equals to W3, right? If you are writing a 4-order polynomial, and similarly, you can simply understand this is y hat. It is nothing but the predicted value. So it will be W0 plus W1x and so on and so forth, just plus W4 x power 4. There will be this other term in this, right? Or else everything will be as above, right? So this will be degree 4 polynomial. So we just know that in this case, I'm not sure about what happens after here and what happens after here, right? What happens before here and what happens after this curve. Maybe this curve may go and turn around, but we do not have anything to do with that particular range, I mean, domain of the data. I am dealing with this particular domain. So I am caring about this curve, that this curve may have only 2. So if it has only 2, then we are good to go with 3-degree polynomial. If there are more, then we can also have, 4, 5, 6 degree of polynomials as well for this kind of a data, because in moving forward, it can also have some other twist and turn. We don't have anything to do with that as well, right? So we can fit this data with at least 3-degree polynomial. 3-degree polynomial will give you best results. If you are filling with 2-degree polynomial, maybe it will fit like this, or maybe it will fit like this. That is not a good fit for our model. It has to go like this, right? So we need to do at least 3-degree polynomial for this. Understanding it, right? So the requirement of a polynomial regression is that our least degree, 1-degree polynomial, that is nothing but the linear model, cannot fit the data at its very best, right? So that is why we required polynomial regression, right? Now you have to decide what equation, what degree of the polynomial you have to choose, right? And you have to do experiment with that, and then you have to come up with the correct number. Okay, now I'll tell you how can you do that. Now exactly the same thing you see in when we were doing this mx plus c, we had two weights. But if you're doing 2-degree polynomial or 3-degree polynomial, the number of weights will be increased. If you are using 3-degree polynomial, so there will be 4 weights, right? If you are doing 4-degree polynomial, there will be 5 weights. So 4-degree polynomial, right? So let's say degree. So 4-degree polynomial, there will be 4 coefficients and 1 intercept. One intercept will always be there. In 1-degree polynomial, 1 coefficient, 1 intercept. In 2-degree polynomial, 2 coefficients and 1 intercept. In 3-degree polynomial, 3 coefficients and 1 intercept, right? So similarly, there will be if a 3-degree polynomial, 4 weights, 4-degree polynomial, 5 weights. Now once again, if you follow the same approach that we had followed in the previous session, so what will happen, it is going to have, the data that is in there, it is going to take just a fixed number of weights. Okay, for example, if you are implementing a square quadratic equation on that, so you cannot increase. If you are going to increase, you have to change the whole code. So that is why in this case we will be going through the functional approach. We'll be going through the functional approach. So functional approach means we will create function for each and every task in there. For example, if you are going to do weight updation, or for example, if you are going to do random weight initialization, right? So for random weight initialization, we can create a function that will return us an array. If I pass, let's say 3, so it will return us a 3 randomly generated numbers, an array, right? Similarly, our data will be also in the array form, so that we can multiply and get the results as a y, right? So this is the thing in here. So as of now, you understood the requirement where we'll be using the polynomial regression and what degree of polynomial equation you will be using. Basically, we are just increasing the degree of the linear equation that will become polynomial, and everything fundamental will be still the same, right? Our methodology will be different in terms of functionality. The core will be still the same. We'll be still using the gradient descent algorithm for optimization. Once we got the weights, we will be optimizing it with the gradient descent algorithm. Okay, all right. So are you able to understand this, right? So let me just give you the coding implementation of this one as well. For this, we have basically gone through. Let me just share the different screen for it. Okay, so I'll just show you this particular thing. How can you do the same, in your case? So we'll be doing the function approximation. We know a function is nothing but, let's say we'll be taking the sine curve, a particular domain of the sine curve, not the whole sine. Okay. And we'll be writing function for each and everything. So I have already written that. I'll just show you how you can do that. Okay. I'll just make you familiarize with the code. When you have to choose, whether you have to go with the polynomial or regression. So let's say if you are just visualize the data, if you think that it is achievable, right, by a line, if you think that you can fit the trend by a line, then that is very well, right? Then you can go. or else you need to understand that let's create a linear regression model and see. Basically, you creating the linear regression model, you'll not be able to achieve very good results. So in that case, you will get a very high error. Okay, if you are getting very high error, that means if you are getting very high error, that simply means that your model is underfitting, and linear regression will definitely underfit in that particular situation. So you can go with the polynomial regression in this. So thank you so much for watching this video. If you liked it, do press the like button and subscribe to the channel, and follow my data science, machine learning, and Python lecture series for more. Thank you so much. We'll see you again in the next one. Till then, bye bye and have a great day.